to show that what you're really doing in this previous picture is the things defined on overlaps, but it's really a concept which the check representation is when you have your space covered by open sets and your things are represented as overlaps. But the thing you're trying to get at is the cohomology. And the cohomology is the object which is represented by these particular functions on all of the overlaps. Now you see, this is just to show you what I was being interviewed by a television company, and they're talking about twistor theory, and they said, well, what good is it? And I said, well, you can solve it. You can solve Maxwell's equations with it, you see, electromagnetism. And they said, oh, how about? And well, it uses this idea called cohomology. And they said, oh, what's that? That should be interesting. There's no way I can explain cohomology. No, not at that level. And then the next morning I realized there is a way, and here's the way you describe it. It's something where the cohomology is the global thing, and you have these representations of it. By piecing this together, you might cut that thing up into pieces, and your check cohomology element would be telling you how to glue the pieces together, and the cohomology is what you extract from that. And here you see it's this non-possibility of the object. But now you're not talking about a three-dimensional object as represented here, apparently, but you're talking about functions, holomorphic things, and you patch them together, and there's an incompatibility about the thing as a whole. This actually relates to... I haven't got the thing going here. That's it. And it actually does directly relate to physics in a curious way. This is a non-locality that people don't sort of emphasize. I mean, Einstein pointed out a long time ago. Let's imagine that you have a source of a photon, which is the thing at the left here, and you have a screen here, and the screen detects whether the photon it makes a spot, say, wherever it reaches. And the point is that you see the screen here is sort of perpendicular to the line here, which means that if a photon is detected here, then to see that it's not detected here, you see this is the point. The detection here prevents it from being detected down here. But there's no signal from here to here that can say, whoops, I've seen it, too late for you to see it. That signal would have to travel faster than light. So that there's something non-local about even this in the representation of quantum mechanics when you start making measurements. So the idea was that you see first cohomology is this kind of non-locality already in the twistor functions. I don't want to continue that here, but that's an idea. This idea continues further. I want to show the thing at the bottom, which is how you piece together now curved twistor space, where locally the patches are flat twistor spaces. The construction at the top is using bundles over this. This is Richard Ward's way of constructing all the self-dual Yang-Mills fields, and which was developed from the earlier construction I had for all the self-dual, anti-self-dual, I guess it is with the conventions, anti-self-dual solutions of the Einstein equations by patching together in this sort of way. Let me be a little bit more explicit about what's going on by going to the next slide. Here we have, at the top, let me just say this. The top picture is flat twistor space, and we have at the right the twistor space, and on the left the space-time, and the points are represented by these Riemann spheres. Now you have to imagine this is a complex projective space, and so what looks like a straight line is really a Riemann sphere. So you have to think, as though I've drawn it as a line, this topologically is a sphere. It's a Riemann sphere. And these represent the points in the Minkowski space. Well, it's a complexified Minkowski space. So the points here are these Riemann spheres, which are represented by lines. And the condition for these points to be null separated, lying on the same null line, is that these lines meet. So you see this correspondence, which works for a Minkowski space. Now what we want to do, at least locally, I mean locally for a point here, which means a tubular neighborhood of one of these Riemann spheres or lines here. So that's what I'm considering. And now we forget about the rest of the space. We're just concerned with this local neighborhood of a point in space-time, this tubular neighborhood. And then we want to deform it by cutting it into two pieces. It could be more. You see there's many patches. But let's say just two, which I slide away from each other and glue them back together again. So I preserve the twistor structure, but now there's something strange about it. And what you find is that what used to be the lines don't glue together anymore, so they're broken. So you say, well, where are the lines? Well, you say, well, there have to be holomorphic curves, which are topologically spheres, and which belong to the same continuous family that you started with. And there's a wonderful theorem of Kodara which says that if your deformation is not too big, then you do have these lines, and we have a 4-parameter family of these lines, and then these lines, each of those, they're the Riemann spheres again, each of those represent points, and you've now got a 4-dimensional space here, and this 4-dimensional space comes out as automatically anti-self-dual, and it satisfies the Einstein equations if you have this projection down like this. Now, this was when I was thinking about Einstein's theory without cosmological constant. If you have a cosmological constant, then it's not just a projection like here, and I should say Richard Ward repeated this construction looking at the cosmological case with a cosmological constant, and instead of having this projection, you have to have this... No, I've forgotten how to move this ahead. Or at least there we go. Now, the infinity twistor is this thing I, which represents the point at infinity, which gives you the space-time, the Euclidean, the Minkowski space rather than the conformal space. And now I've put in, which is not the usual infinity twistors that twistor theorists have been brought up with, but the one where I have a cosmological constant in it. And this cosmological constant took me a long time to be convinced that it's really there, but then I became persuaded, and I'm glad I did, because the things I want to say later depend utterly on the presence of a cosmological constant. If it were not there, and if it were not positive, the thing would not work. So the theory depends on having an infinity twistor in which there is a positive cosmological constant. I think that's got missing at the bottom. Can I bring it back? I'm not sure. Yes, I have brought it back. So what we see is not just the infinity twistor, which used to be singular. It now gives you a proper symplectic structure. It's a skew thing, which is non-degenerate. And if you contract it onto itself, that's its dual or its complex conjugate, you get the cosmological constant and not zero. And I have this form now at the bottom, which involves the cosmological constant, the infinity twistor, both ways up, and you have it in terms of the z's and the w's. What are the w's? Well, the w's are the z bars. They're the complex conjugates of the z's, but now I free them up. So a lot of twistor theory is useful to think of your complex conjugates as a separate variable, and then when you're looking at the real space-time, you make w's complex conjugates of z. But you play around them as being separate, independent objects, and only at the end, when you talk about real space-time, do you make the w's be the complex conjugates of the z's. But still, that is capital theta is the 2 form, which is now non-degenerate 2 form. You need both bits, you need the cosmological constant, and it took me a long time to realize not only do you need the cosmological constant, but you need both bits. Have all that, then the things that I want to tell you seems to work. Okay, let's continue with this. Now, this is the main stumbling block. For about 40 years, this was what held up twistor theory, as far as I was concerned. Thing called the googly problem. It's a very appropriate term if you know anything about cricket, and I'm not supposing you do necessarily. But this is a ball which is bowled. It spins about its axis. Americans will say, oh, it's a screwball. No, it's not a screwball, because in baseball, the ball doesn't bounce. In cricket, the ball bounces, and so you have to notice whether the spin is spinning right-handed or left-handed, and that's the important thing. And the framework of twistor theory was sort of geared to have it spin one way. And what's called a googly is a ball which is bowled, which spins the other way, even though it looks as though it spins the same way. So it's within the framework of the left-handed spin, how do you describe the right-handed spin? And that's the googly problem, which held the whole subject up for 40 years. I had what I thought was a very beautiful solution, which depended on the cosmological constant being zero. So I was resistant for a long time to the cosmological constant, but then I became persuaded. I think it was Jerry Ostreicher persuaded me it was not just a supernovae. It really, you need it to make lots of things work in cosmology. So now, here's the other thing that we need, the non-commutative twistor algebra. Now you see, I'll come to the reason for this shortly, but it's been a thing which you kept noticing all the way through twistor theory, that there seems to be useful to think about the complex conjugate of the twistor when you're bringing in quantum mechanics or something like that. The complex conjugate really becomes also the canonical conjugate. So we now think of the complex conjugate as a non-commuting object with the twistor itself, and the commutation rules are written at the top, and then you have to make sure that you write your helicity quantity, that's little s, as split into the sum of the two things at the bottom, which I'm not very good at getting this thing to work, so let me, oh dear, what have I done? Here we have the ZZ bar has to split up, and this is the helicity operator. And then your momentum and angular momentum have the commutation rules of standard quantum mechanics, so it ties in beautifully with that. It ties in with the contour integrals I wrote before and all sorts of things. So it's a very natural algebra to introduce the non-commutative algebra where the complex conjugate of the twistor now becomes a canonical conjugate of it. So that's an important part of it. Now, the solution of this googly problem, in my view, came about from a discussion I had with Michael Atiyah, and I was trying to see how on earth you could build up a space of a sort where you didn't have the points. The whole problem was that if you have the points in the twistor space, you have these things called alpha planes, and the alpha planes are the things which give you the thing being anti-self-dual. So you're stuck with the thing being left-handed. And so I finally came around to the view that you've got to have a thing which is a space of a sort, but it doesn't have any points in it. And so the problem was, how on earth do you do that? And you do that using somehow the algebra of the functions. You want to say these are holomorphic in some sense, so you have the algebra of holomorphic functions, and you want to patch the algebras and not the points. And I had this conversation with Michael Atiyah and said, well, look, how do I make a space where I somehow don't have the space and I want to patch the algebras? And he looked at me and said, well, that doesn't work. And I sort of knew that, because if it doesn't work, because the prime ideals give you the points and all that. But then he said, after a slight hesitation, but that's not true if you have a non-commutative algebra. And I thought, wow, because it's the non-commutative twistor algebra that you have to patch. And that's the key point. So what I'm trying to do is patch together, do bits of twistor space in the same way as before, but it's not the spaces I patch, it's these non-commutative twistor algebras that I patch. And that's the key thing. So that is what palatial twistor theory is about. Now let me try and see if I can describe the ideas quickly. Now you see, one of the things I found troublesome here is that it's algebras. Okay, I can play with algebras a bit, but I don't have the sort of intuition about algebras that I ought to have. But you see, here's the key thing. You can think of these algebras as being the algebras that you get from geometric quantization. Now, the beauty here, I think Nick Woodhouse pointed this out in his book, but let me just remind you and myself what it was about. You see, in twistor theory, you have, remember, the space divided into two, and you have the space in the middle, which represents the light rays. The space in the middle, in projective space, the points represent light rays. But if you think of it as non-projective, then the light rays have a scale. So there's scaled light rays. That gives you got a momentum as well. This makes it a symplectic space. And if it's a symplectic space, then you can consider doing this process of geometric quantization, which gives you a sort of quantum algebra. So that's the idea. And what's the first thing you do? The first thing you do is to construct a circle bundle over this space. Thank you. And this circle bundle is, well, the beauty of it here is that if you go, which I'll call a little p of n, that's the non-projective in the sense you've scaled with a real scale the light ray, so it's got a momentum attached to it, which is a scaling. But now what you have to do for geometric quantization is to introduce a phase as well. And the thing, you've automatically got the phase in twistor theory. That's the beauty of it. It only applies in this number of dimensions, which I like too. It means it only works properly if you're in space-time of 3 + 1 dimensions, which seems to me the right thing to do. And here you have the phase automatically sitting there, because in twistor theory, if you're looking at the twistor as a whole, not just the projective twistor, but the actual twistor, the null twistor the space of these things is a circle bundle over the space of the symplectic space. And so you're in the right place to do this geometric quantization. Now the thing